Alright guys, so today we're going to continue our discussion of diagramming covalently bound molecules by drawing Lewis structures. So we want to start off today by drawing some of the Lewis structures for some of the polyatomic ions that we've learned. So let's start off by drawing the Lewis structure for ammonium. Okay. So we'll still continue to use the same steps that we always have here for drawing the Lewis structures. First, we'll determine the number of atoms and the type of atoms we have present. So for ammonium, we know the formula is NH4 with a +1 charge. So there is 1 nitrogen and 4 hydrogens. So we want to determine the total number of electrons present. So nitrogen is in group 5. So we have 5 plus, I'll just say 4 times 1. So that equals 9. But we know that for a positive 1 charge, we subtract an electron. Okay? So in order to have a positive charge here, you have to have more protons than you do electrons. So 1 was lost somewhere, or we could consider that there is 1 fewer than there would be if it were neutral. So we can say there are 8 electrons present. So if there were a negative charge, we would add electrons for every negative charge that we have. So now we want to decide the central atom. So it should be pretty obvious here. Hydrogen cannot be the central atom. Okay, so we connect the nitrogen and the hydrogens. Okay, so I use 2, 4, 6, 8. I already used 8 electrons. Okay. So if I did this correctly, I should be done. So now I need to go back and double check a couple of things. First, I'll check the total number of electrons used. I used 2, 4, 6, 8. I'm in good shape there. Nitrogen has 2, 4, 6, 8 electrons, so it's good. Each hydrogen has 2 electrons, so I'm in good shape there. So we're almost done. One new step though, we haven't learned yet we haven't learned yet how to place this positive charge. So we don't know which of these atoms contains or possesses the positive charge. So what we'll do is when we have a Lewis structure that has a positive or negative charge, we'll put it in brackets and we'll put the charge outside the brackets. So this positive outside the bracket just tells me somewhere on this structure there is a positive charge. Okay, we don't have to show where it is just yet. Okay, so let's look at another one. Let's look at hydroxide. Okay, so the number and type of atoms, so it's OH -1, so 1 oxygen, 1 hydrogen. So oxygen is group 6, so I have 6 plus 1 for hydrogen, that's 7 electrons, but I have a -1 charge, so I add 1 electron, so I get a total of 8. There's only 2 atoms, so the configuration doesn't matter. I could draw it like this, or like this, it doesn't really matter. Okay, so I'm going to do 2, these will both be the same answer, you can just flip it around. So I already used 2 electrons. Okay, so I have 6 electrons left over I have to place in the form of lone pair electrons. So hydrogen doesn't need them. Hydrogen already has 2 electrons, so it's good. So put it on oxygen. 1, 2, 3, 4, 5, 6. I'll do the same over here. So let's go back and check both things. First, I check I use the correct number of total electrons. 1, 2, 3, 4, 5, 6, 7, 8. So I'm good. And the other one's the exact same. Then oxygen has 8 electrons around it. Hydrogen has 2 electrons around it. So I'm in good shape. And I can't forget to put the brackets with a -1 charge, showing there's a -1 charge somewhere on that molecule there. So let's look at one more. Let's look at nitrate. Okay, so I have NO3 -1. Okay, so I need to go through and determine the number of electrons. So nitrogen would have 5 valence electrons. So 5 plus 3 times 6. So then I'll go ahead and add the 1 electron there for the -1 charge. Okay, so I'll see that in total I have 24 electrons. So if you had forgotten to add this 1 electron for the charge, you would have gotten an odd number of electrons. So it's very rare that you get an odd number of electrons. So if you do, go back and double check your work to make sure you're on the right track there. So I determine my central atom. So I determine that is nitrogen. So I'll place the oxygens around the central atom. Again, if you wanted to flip the configuration, put an oxygen on bottom, that's perfectly fine as well. So I connect it. Okay. So then I do 24, I use 2, 4, 6. minus 6. Then I have 18 left over. So I have 18 left over, so I'll just go ahead and try placing them around the oxygens. That'll give each oxygen 6. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so that looks good. All the oxygens are satisfied. But nitrogen here only has 2, 4, 6 electrons, so that's not good. So there's no way to place these electrons and have it work out properly. Okay, so there's a little bit of an issue here. So if I can't make that work out, remember step 2 is to go back and try a double bond somewhere. Okay, so I'm back in the same place. I have 18 electrons left over here after I connect it. So I'll just try making one of these a double bond. Okay, so now I have 16 electrons left over. So now nitrogen's good. This oxygen needs 4. So I put 1, 2, 3, 4. Sorry about that mark, that was not an electron right there. So then these oxygens each need 6. So now this is looking better. Nitrogen has 8, this oxygen has 8, this oxygen has 8, this oxygen has 8. So we're in good shape. So let's go back and double check, make sure I use the correct number of electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I'm in good shape now, so that's the correct answer. Okay. So nitrate has a -1 charge. Okay. So that is the correct answer for the Lewis structure for the polyatomic ion of nitrate. So you'll see that drawing the polyatomic ions, nothing really changes other than having a charge. So when you have a charge, just account for either the gain or loss of electrons there. So you might be asking why I chose to put the double bond here versus the double bond right here. And the answer is, I just kind of randomly chose it. But that kind of leads us to our next idea. So it is the idea of resonance. Okay. So let me redraw nitrate on this paper. So I drew nitrate like this. But I also could have drawn nitrate like this. And so I know you're saying, well, you just rotated the molecule. But think about it as if I didn't rotate the molecule. So let's just I'll just color this oxygen pink. So let's say the pink oxygen is the pink oxygen over here. So now I have the double bond on a different oxygen. Okay, so I could have done the same thing, or done a different thing rather, and got an equally valid answer. So I could have done this. I could have double bonded this nitrogen and oxygen together. Okay. This answer is also perfectly valid. Okay, so this is what we call resonance. So resonance is the idea that when you have a Lewis structure like this, where electrons can be in different places on different atoms and each give a completely valid Lewis structure, then the actual Lewis structure is some combination, okay, of all the contributing Lewis structures. So another way to show this is I could do this. Okay, so I know in all these structures I have single bonds connecting these. So I can also show this. So showing that dashed line just tells me, okay, well, sometimes there's a double bond here, sometimes there's not. Sometimes a double bond here, sometimes there's not. Sometimes a double bond here, sometimes there's not. Okay. So when we draw it like this to kind of show the combination of the resonant structures, which is what we call this, we can't actually show the lone pair electrons because those also differ. So just be aware if you see these dashed line bonds, that refers to a structure where the double bond could be here, but it could also be somewhere else. Okay. So let's look at one more example of resonance. Let's look at O3, which is known as ozone. Okay. So O3 has 3 oxygens. So there are 3 times 6, 18 electrons. So remember that we really don't want to form closed structures unless we have carbon, and that's a rare case for this class at least. So we just want to have the oxygens in a row. So I go ahead and I connect them. So I used 4, so I have 14 electrons left over. So if you try to place the 14 electrons, you can try it on your own. You'll find there is no way to give all oxygens 8 electrons only using lone pairs. So I have to go back, I have to use a lone pair there. So then I can place my electrons. So now I've used 2, 4, 6. So I have 12 electrons left. So I can do 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. So now I go back and check, did I use enough electrons? 2, 4, 6, 8, 10, 12, 14, 16, 18. I'm good there. This oxygen has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. So that's a perfectly valid Lewis structure for oxygen. It's a correct answer, but there's also another correct answer. Notice I didn't use brackets here. You only use brackets when there is a formal charge on a structure. So I could also have done this. So again, think about this not as the molecule flipping, but as the electrons being in different places. So I could label that pink oxygen there. So both of these are perfectly valid structures, okay? They are just resonance structures, so the electrons can be located in different places. So really all we need to be concerned about now as far as resonance goes is if we have more than one possible valid answer, we need to show all the possible valid answers. When you take either organic chemistry in college or my senior class, it'll be very important that we consider resonance when we look at organic reactions. A lot of organic reactions and organic molecules rely heavily on resonance. So we'll actually show how the electrons move to get from one resonance structure to the other. But for now, we need to be concerned about if there is more than one correct valid answer, we need to show that correct valid answer. And if that valid Lewis structure has a negative charge or a positive charge, we show that in brackets. Okay. So let's look at one more polyatomic ion. I know there's probably not room for this, so just kind of make this in the margin somewhere. We haven't looked at any of the elements that are exceptions to the octet rule yet, besides hydrogen, and that's a common exception. We haven't seen one of the molecules that can form more than one, or can have more than 8 electrons in their valence shell. So let's look at one of those. Let's look at the polyatomic ion sulfate. Okay, so we have SO4 with a negative 2 charge. So sulfur and oxygen are each in the 6A column, so they each have 6 valence electrons. So there are 4 oxygens and 1 sulfur, so I can say 6 times 5 plus 2, and the plus 2 is for the 2 extra electrons there. So 6 times 5 is 30, plus 2 is 32 electrons. Okay. So we see that sulfur here is likely going to be the central atom. So I have sulfur, oxygen, 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 oxygen. Okay. So I connect them. So if we have 32 electrons that we have to use, I've already used 2, 4, 6, 8 of them. So I can say minus 8. So 32 minus 8. I get 24 electrons. Okay. So if you were to place 24 electrons, so that would be 6 around each of these oxygens, you would have a valid Lewis structure based on what we've learned. Okay. Everything would have 8. But we know sulfur likes to have more than 8 electrons. Sulfur likes to expand its valence shell. So this is kind of an example where you just need to be familiar with the structure of sulfate, because without knowing where the charges are, it's kind of difficult to predict the structure. So I'll show you what the actual structure for sulfate is. So this is the structure for sulfate. And the reason that we have to have these double bonds and we can't have just electrons around oxygen is that would give us a charge that would not be -2. It would give us a -4 charge. We really don't know enough right now in this class to be able to predict that charge. So for right now, just take me at my word for that. We'll discuss later how to determine which atoms actually have that charge. So you should recognize that sulfur has an expanded octet here. It has 2, 4, 6, 8, 10, 12 electrons. So if you remember back to your rules, that's perfectly okay for sulfur. Sulfur can have an expanded octet. So then you should probably recognize this is also a resonance structure. So I placed the double bonds here and here kind of arbitrarily. I could have flipped it around and put them here and here. So I could also draw the other resonance structures, okay? So just for now, just be aware this is the structure of sulfate, and we'll come back later to looking at some of the exceptions to the rules and how to know when we expand the valency or when we have an expanded octet and where to place these positive and negative charges. So, but for now, let's worry about the simpler cases, things like nitrate and ammonium, and then let's also worry about the simple resonance examples. So one other thing that we want to touch on right now before we look at ionic bonds is what we call a coordinate covalent bond. So a coordinate covalent bond is kind of a special case where you have a covalent bond between a metal and a nonmetal. So it looks something kind of like this. You might have an iron, for example, and it might have 6 hydroxides bonded to it. So that's kind of counterintuitive to what we have discussed so far. We said that metals and nonmetals typically form ionic bonds, so that's true. But there are special cases when you have coordinate covalent bonds where nonmetals do actually bond to a metal covalently. So a couple of terms we want to learn here. When we have a coordinate covalent bond, which is just a nonmetal bound to a metal, so I could have also shown the oxygen and hydrogen bonded together. We'll just say these are hydroxides bonded. We have the term ligand. Okay? So the ligand is what is bound to the metal. Okay, so in this case, the hydroxide would be the ligand, and there are 6 of them. And we also want to call this a dative bond. So a dative bond is a special type of covalent bond where one of the atoms involved in the bond provides both of the electrons being shared. So we'll define it as one of the bonding atoms provide both shared electrons. Okay, so most of the examples of covalent bonds, each of the atoms provide one of the electrons being shared, because we know that each covalent bond has 2 electrons. But when you have a coordinate covalent bond, typically you see dative bonding. So the hydroxide, the nonmetal here, would provide both of the electrons for that covalent bond. Okay, so that's really all we're going to look at as far as coordinate covalent bonds go. If you take a higher level chemistry class, you'll discuss this at length. Typically, these coordinate covalent compounds form pretty intense colors, so they form colored solutions that we can look at and discuss in the class at another level. But for now, just be aware of the terms coordinate covalent bond, ligands, and dative bonds, and be able to apply them and know what they mean here. Okay, so that's pretty much all we're going to discuss for now as far as covalent bonds go. So in the next video, we'll begin to talk about ionic and metallic bonds. Then we'll come back to covalent bonds in a couple of days and talk about the geometry of molecules. So when we say what is a molecule's geometry, that means what is its shape. So we know that all molecules aren't flat like we draw them on the page, so we need to have a discussion of what's their actual three-dimensional shape. But before we do that, let's take a day or two and discuss ionic and covalent bonding next and what that looks like and how we actually diagram that on the paper.